All right, hey everybody. Today we're going to talk about acids and bases. We're going to begin our discussion on that. It's a very large topic. And so one of the things you were asked to learn about in your web quest was different ways to define acids and bases. And so here's the three definitions. I'm going to go over those three with you real quick. We have the Arrhenius definition, Bronsted-Lowry, and Lewis definition. So let's start with the Arrhenius definition of acids and bases. So I'm going to show you that they both work pretty much the same way. We have a compound that dissolves, and you have to remember that in all cases we're talking about dissolving in water. So some compounds dissolve in water to form acids, and some compounds dissolve in water to form bases. And so if a compound dissolves in water and forms hydrogen ions and some other negative ion, it'll be an acid. If the compound dissolves and forms hydroxide ions, so these are hydroxide, and some other positive ion, then we'll get a base. And so here's an example of each of those. So if we have hydrogen chloride dissolving in water, the water is going to be able to break that apart into two separate ions, a hydrogen ion and a chloride ion. The same thing with sodium hydroxide. If we put sodium hydroxide in water, the water will separate that into two separate ions, a sodium ion and a hydroxide ion. These are what make ions acidic. This is what makes solutions acidic. These are what make solutions basic, hydroxide ions. These don't really have anything to do with acid and base. They're just there. So that is the Arrhenius definition. These compounds decompose as they dissolve and form either hydrogen ions or hydroxide ions. Okay, so let's look at the Bronsted-Lowry definition. We're still talking about positive and negative ions, acids and bases, but we're not defining them by decomposition. Instead, we're talking about protons moving from one compound to another. So it's like this. Here's an acid and here's a proton. It says H+. That's a proton. That means a hydrogen atom has lost an electron, and that's all that's left is a proton. So that's why we symbolize it H+. But if these two compounds were in water, an acid will donate that proton to a base. So that's the proton donor and the proton receiver. So here's an example. We have water and ammonia. Ammonia is a compound that's in a lot of cleaning products. So in this case, water is actually an acid. It's got a proton and it's going to donate that to ammonia. So let's think about that. Water has H's in it. A protein is a hydrogen ion. So if we take that H away and give it to ammonia, what do we have left? We have OH minus. And see how that changed colors? This is now a base. It's a hydroxide ion. Whereas the ammonia gained that proton. And now it has another H. It has four H's, and it changed colors too. Now it's an acid. This is called a conjugate base and a conjugate acid. So a conjugate base and a conjugate acid. Now this is reversible. So the proton, the extra proton's over here now, it could go back the other way, and so that we can come back to the original ammonia in water. So here's another example. Iotic acid is HI, high. And in water, a proton's going to move. Now in this case, water is actually a base. See, it's purple. The iotic acid is going to donate that proton to water. That H right there is the one that was lost, and so it becomes an I minus, an iodide ion. Now this water is gaining an extra H, so it becomes what's called a hydronium ion. Hydronium ion. So this is the conjugate base and this is the conjugate acid. And again, that can go back and forth. That proton can go from here back to here, and we go back to these two. Now this is actually still similar to the Arrhenius definition. We're still actually seeing the HI separate into ions. That's still happening. The difference is the Bronsted-Lowry definition is telling us what happens to that H after this happens, and that's where this happens. The H is going to the water, we're getting hydronium. So the Bronsted-Lowry definition is just a little bit more complete. Okay, Lewis definition. Oops, I got a little teardrop on there. Okay, so Lewis definition is similar, except instead of protons moving, we're talking about electrons moving. So bases are electron donors. And it's usually a pair of electrons that's being donated. So the acid just received a pair of electrons. So here's an example. We have H, positive hydrogen ion and a hydroxide ion. And so the OH, the hydroxide, has a pair of electrons to give away, and it's going to give it to the hydrogen ion, and that'll form water. So here's the Lewis structure for this. So here's the hydroxide. Here's an oxygen with 6 unshared pairs of electrons. Here's a shared pair of electrons. And there's the proton. And so let's say these are the 2 electrons that are actually going to transfer. So they're going to go over here, right? And so we have a proton and 2 electrons. And so what happens is we have this negatively charged thing and this now positively charged thing, and opposite charges attract. And so the water, see that line right there, that's these 2 electrons. That's a new shared pair of electrons. So we formed a new covalent compound to form this, a new covalent bond to form this new compound, which is water. Okay, so Lewis, acids and bases, we're watching electrons move around. In Bronsted-Lowry acids and bases, we're watching protons move around. Okay, so let's start talking about something called pH. So how do we actually know if something is acidic or basic? So we have this scale with which to measure pH. So pH scales go from 0 to 14, and on the left side from 0 up to just before 7, so we could have like 6.99, that's an acid. 7.1 all the way over to 14 is bases, and right in the middle is 7, which is considered neutral. I have that written here as neutral. So before we go any further, I need to explain to you something about the word strong and weak, because a lot of people confuse those terms and think that these over here are very strong acids and these are weak acids, but that's not true. Okay, strong versus weak acids. Here's how that works. So here's hydrogen chloride again, and if we put that in water, here's some lumpy water molecules. Water can pull these apart, okay, and it can pull them apart very easily because they have very weak bonds. The HCl has very weak bonds, so it's very easy for that to happen. And the result is we get these 2 ions. That will happen 100% of the time. See, the negative of the water is attracted to the positive of the water is attracted to the negative, chloride. That'll happen all the time because of this weak bond. But if you have something like carbonic acid, there's a much stronger bond between the H's and the CO3s. Water can pull these apart sometimes, just not as much as with a strong acid. So it struggles. It has a very hard time pulling apart these covalent bonds. A small percentage of them will pull apart, and we'll get these positive and negative ions. So we do get some hydrogen ions, but very few, so it tends to be, that's why we call it weak. Now, strong bases, they work just the same as, there we go. They work just the same as the strong acids. So here's NaOH, sodium hydroxide. It's a very strong base, and that's for the same reason, because it's very easy for water to pull these apart, right? And then we get these ions. We get the hydroxide ions. That's what makes something a base. That happens 100% of the time. Weak bases don't. So weak base, this boron hydroxide, is very tough for water to pull apart. Only a very small percentage will actually break down into hydroxide ions. Now, ammonia doesn't have OHs in its formula. It's just NH3. And so what happens there when we put this into water, remember this is the one. This is the one where protons move back and forth. Right? So a proton would move this way, and we get not on this one. We get NH4 plus, and we get OH minus. But remember that this is reversible. So here's my NH4 plus. So this is reversible, and that's actually what happens is the reverse of this happens more often than the forward one does. So this is the forward one where we get this, we get hydroxides, but the reverse happens more often. So we end up having this and fewer hydroxides. So that's why it's a weak base, because it doesn't produce very many hydroxides. Okay, so that's what weak and strong means. When we're talking about pH, we can't use the word weak and strong. We have to use the word concentrated and dilute. So here's what that means. So look at my little legend here. I've got orange dots and blue dots. The orange ones are hydrogen ions, the blue ones are hydroxides. This is a beaker full of water, and I put some hydrogen ions in there, some kind of acid, and there's lots of hydrogen ions. So this has a very low pH. If I want to change the pH and raise it up to a dilute acid, I would have fewer hydrogen ions and relatively more blue ions. If I was going to have a neutral, so I've got 4 orange ones in there and 3 blue ones. If I was going to have a neutral solution, that means I have an equal number of hydrogens and hydroxides. That's what neutral means, and that has a pH of 7. If I have a dilute base, I'm going to have just a few more blues than oranges. If I'm going to have a concentrated base, I'm going to have a lot of blues and very few oranges. Okay? So these are the very concentrated bases. These are the dangerous ones. Concentrated acids, these are the dangerous ones. Okay, so on to how can we actually tell if a solution is an acid or a base or not? There's a lot of different ways to do that. One of those is with indicators, and those are just chemicals. And those chemicals will change color in the presence of acids and bases. So the first one I want to show you is litmus paper. Okay, so I've got these test tubes arranged here, and I've got acids in these 2 test tubes, bases in these 2, and the middle one is just water, it's neutral. Okay, and so what I'm going to do is I'm going to put some litmus paper in those. And that's just paper that's been soaked in a chemical indicator. Okay, and you learned in your web quest that blue litmus paper with an acid should turn red, and it does. Now, if we did that with a red piece of litmus paper in an acid, nothing happens, it just stays red. So here's a base. We put a blue one in a base, nothing happens. If I put a red one in a base, it changes blue. So that's all litmus paper does. It just tells you if it's an acid or a base, but it doesn't tell you anything about pH. So we do have another indicator, a really common indicator that kind of does the same thing. So I've got an indicator called phenolphthalein. Excuse me. Phenolphthalein, okay? And what that does is it just turns pink in the presence of hydroxide ions, so a base. All right, so I've got an acid and a base here. Okay, and what I'm going to do is I'm going to put this indicator, just a drop, into the acid. Would you expect to see any changes? No, because this is an acid. There's no hydroxide, or very few hydroxides in there. So what I'm going to do is I'm going to pour this base into this acid, and it's going to turn pink once there's more hydroxides than hydrogens. Okay, so let's watch. Pouring the base into the acid. Okay, so it's all pink now, and that's because there's more hydroxides. So this is not an acid anymore. This is now a base, and I know that because the indicator is telling me that. Now, what would happen if I poured this base into a concentrated acid? So look at that, it's staying clear. It's staying clear because there's still more hydrogens than hydroxides. So all that phenolphthalein does is it tells you if something is an acid or a base. That's it. It's just like litmus paper. So here's another way to tell. So we have some indicators that will actually tell us what the pH is. So like I said, in these test tubes, I've got acids and bases in a neutral. And I've got this indicator here that will actually turn different colors depending on the pH. Reds and oranges mean acid. Greens and blues mean base. Okay, so I'm going to start here with this acid, which is actually a concentrated acid. See how red that is? It's very red, so that's a concentrated acid. Here's a dilute acid. So that's kind of orangey. This is neutral, right? It's just water. So that's yellow. Now let's go to a dilute base. This is baking soda and water. It's a dilute base. So it's kind of a green-blue color. Here's a concentrated base, which is ammonia. So it's a very blue color. So we end up with this really cool looking rainbow. It's all the same indicator, but it's telling me that different pHs. So I probably have a 1 or a 2, like a 3 or a 4. This is a 7, maybe an 8 or a 9, and this is like a 12 or 13. So if we don't want to use indicators, we can use technology. So right now I have this probe in water. So we could expect that to be somewhere around a pH of 7. It's been off for a while. So if I let that sit there for a while, it'd climb back up to a 7. I'd have to stir it because it's just water. Now, what if I put that into the acid? So I poured some hydroxide in here, so it's not going to be super low, but it's pretty low. So this probe is telling me the exact pH. 1.9, what does that mean? So 1.9, that's way down here. That's right about there. So that's a concentrated acid. Now what if I put that, where's my pink one? Here's my pink base. So let's see what the pH of the base is. So look at that. It climbed up to 11.6. 11.7, so what does that mean? 11.7 is right about here, so that's a pretty concentrated base. And that can change if I added some acid to that. Let's watch what happens if I add some acid to this base. Look at that, we're watching the pH drop, and look at it, it went from pink to clear because it's not a base anymore. Okay, so begins our discussion on acids and bases.